Peterson was trying to do. She didn't think, and if you look at this, this doesn't match yours, for example, right after example 3 where it says elementary row operations in row echelon form. It's really hard to fit these instructions up here, so what she did was she shifted them all down by 1. But I'm with you in that it kind of makes it confusing when you do that. So what she was saying was we'd start with this matrix and multiply equation 1 by -3 and add it to 2. So I think I'm just going to keep my notes like this, but she said it didn't show up really well in the packet. If she splits it over, I can see that. Yeah, your margins, bless you, wouldn't be big enough, so it probably wouldn't have shown up on yours. The other thing, would it be best to just take the blue off? And just start without it, or does that help you in the notes?
No, not at all. It's a good idea.
Okay, so maybe when we have our next PLC. Yeah, because the instructions weren't in the right kind of order here. Maybe it's just best to leave those off.
Yeah.
And just go without it. Okay. Okay. Yeah. Good to know for next year. Get those instructions off there. Because what we want to do today is continue on with that, and we did go through a lot of this and got down to problem 4, and I ran out of time. And it could be that, you know, we may have to go a little over with 7 for you tomorrow as well. So it'll be one of those times when you do what you can in the homework, and we just kind of stop when we get to something that we don't know. So down here, we were talking about our row echelon form, which was the problem that we just talked about as far as the blue stuff. So like I said, I think a lot of that just made it sound worse than it really is. So with this one, we're supposed to solve the system. And what we want to do is 1s across the diagonal and 0s for anything to the left and below. But we have to get ourselves a matrix before we can do that. And taking that matrix is just taking the x's and y's and z's out, you know, that we don't need. So we write our matrix as 1, -1, 2, -3. And since this would include that -3, this would be called an augmented matrix, because we're going to have those solutions on there as well. So 1, -1, 2, -3 for the first row. 2, 1, -1, and 0 for the second row. -1, 2, -3, and 7 on here. So when we did this by hand with the x's and y's and z's, we picked a terminator, one equation that worked well to get rid of something. And that is kind of the way you want to think when you start these. Because when I look at this, I'm thinking, the 1's already here in this first row. I'm not messing with that. I'm going to leave that there. Because if I have 1's across the diagonal, I'm done. But I need 0's all over here. So if I'm going to use the top row, and I'm going to try and get rid of the second row here, what should I do to row 1 to eliminate that 2 in row 2? Multiply by -2. And like I said, it never hurts to actually kind of write those down outside the matrix. So if we multiply 1 times -2, we get -2. -1 times -2 is 2. 2 times -2 is -4. -3 times -2 is 6. And then go ahead and add it. Get your new augmented matrix. But the top one's going to stay exactly as it is, because we said, hey, that one's good. -2 plus 2 gives us our nice 0 that we need there. And then 2 plus 1 gives us 3. -4 plus -1 is -5. And 6 plus 0 is 6. And then we're just leaving that bottom row alone, because I want to do every step separate with you to make sure that this is something everybody can follow. There we go. So what do you see as the next step? What would you want to do to try to get those diagonals of 1 and the 0s? Go after row 3? Okay. Do we have to do anything to row 1 to add it to row 3 to get the 0 that we want? Nothing. We're just going to add. I'm probably going to run out of space if I just keep going down. So now all we're doing is we're taking row 1 and adding it to row 3. 1 and -1 would be 0. -1 plus plus 2 is 1. 2 plus negative 3 is negative 1. Negative 3 plus 7 is 4. Now, something good just happened. I now have a 0 on the left and a 1 here, but I would really want this row and this one, because that would keep my diagonals at 1s going. Can you just take a row and flip it with another? Sure, you can. It's not a big deal. It's like taking an equation and saying, can I put this equation above this equation? Will I still get the same answers? Of course we will. So let's flip that. So really, the first and second rows now are done. So what's your plan on how to get rid of this 3, which needs to be a 0? Multiply row 2 and add. Would it be a good idea to multiply row 1 by something and add? No, because then we're putting numbers back in this position again. So we definitely are going to take row 2 and multiply it by what? Negative 3. So we have to add that. So we're going to take, let me write this down in matrix language here. We're going to take a negative 3 times row 2, and we're going to add it to row 3. That's not going to put any numbers in positions that we don't want them in, and move us closer to what we want. So first row is just fine as it is. Second row, fine just as it is. And some people will just do all of this in their head, but if you find that you're losing stuff when you do that, then actually physically write down what is negative 3 times row 2. So negative 3 times 0 will be 0, negative 3 times 1 will be negative 3, negative 1 times negative 3 is 3, and then negative 3 times 4 would be negative 12, and then add. You don't want to lose out on material just because you try to do too much in your head at one time. So 0 and 0. Negative 3 and 3. Ooh, that's a bonus. Now we've got negative 5 plus 3 and our 6 and negative 12. We're really, really close. So now we have to figure out a way to keep those first 2 rows just like they are. Somehow get this to be a 1. Right here. Well, we can't use the other rows to do it, because if we do that, then there's going to be numbers back in these first 2 columns. So can you think of something we could just do to this row that would give us a 1? Negative 1/2. Multiply by negative 1/2 and you'll have it. So we're going to take negative 1/2 of row 3. Or you could think of it as row 3 divided by negative 2. Do all this. Because these were our x's, these were our y's, these were our z's, and these were answers over there. And now we see our triangular form that they talked about yesterday. And right down here, this says no x's, no y's, but 1z equals 3. Z equals 3. And we'll do that back substitution to say, okay, this one is y minus z equals 4. Well, I now know what z is. Z is 3. So y is 7. And now go right up to the top where we have 1x minus y plus 2z equals negative 3. And you realize we have y and z. So we'll just get those in there. And we'll be able to find x. So we'll have x minus 7 plus 6, which is x minus 1 equals negative 3. We'll add 1, and x is negative 2. And then to round it all out, we're going to write our ordered triple. Negative 2, 7, 3. Beautiful. Now let's just say that the directions didn't say we had to do this by hand. And maybe the directions said, use your graphing calculator to find the row echelon form. Well, some of these people are gone. That means I've got to get my calculator. Grab your calculator while I original matrix into the calculator. And that would be the very first matrix that we wrote. This one right here. So let's go get that one in. And then we'll find that row echelon form. Does everybody remember how to get to matrices? That x to the negative 1 button has those. So second matrix, and we want to edit. So we're going to go over to edit. Number 1. Now this is not a 3 by 3, is it? What's the order for this one? 3 by 4. And then we can enter those in. Looking good. 1, negative 1, 2, negative 3, 2, 1, negative 1, 0, negative 1, 2, negative 3, 7. Now, remember, this is where it stores all the matrix numbers that we have in there, but we have to hit second quit because we're now going to ask the calculator to actually do something with it, and that's on the execution window, and this is the execution window. So now we'll do second x inverse, which is the matrix button, but we want it to do math. So we're going to arrow over to the right just once. And I think sometimes they do this on purpose. REF is hidden from us, so we have to go down and look for it. And there it is. Little teeny REF, which is a capital A. So we're going to hit enter. And then we have to tell it which matrix we want it to do the row echelon form for. So second inverse, and just number 1, because that's where we had our matrix. And I'm going to finish off the parentheses, but I know I wouldn't have to. Enter. So we've got our z equals 3. Now, the question is, why doesn't the rest of the stuff they did, why doesn't it match our row echelon form? There's all kinds of operations you could do to get a row echelon form. They maybe didn't do it the same way that we did, which is pretty obvious because they ended up with fractions here. We don't like fractions, so we tried to do math that would avoid fractions when we went through it. So the problem with row echelon form, especially if we put it on a test, is that everybody could have different row echelon forms, but you get the same answers in the end. You know, it might not look the same at the row echelon form point of the problem, but when you get done, you'll get the same answers. So row echelon form, is the calculator useful? Yeah, we don't use it a whole lot. I mean, usually we do that process of Gaussian elimination, bless you, on our own, and get something that makes sense with integers instead of what the calculator will think is easy, which would be decimals and that kind of stuff. But we would get exactly the same answer, and that's the point. You know, you could use a graphing calculator if you wanted to. Now, how could we take what we already have and work so that we could get x equals y equals z equals without having to do the back substitution? Well, that's called reduced row echelon form. So, like it says, reduced row echelon form, a word of caution, The graphing calculator, you're going to get a different row echelon form than you do. Don't think you're wrong. You know, it's just that you have to keep going. So like it says, fortunately, all row echelon forms will produce the same solution to the system of equations. So whether or not you get the same thing they do or not is not important. So here's what we're going to do. We're going to continue applying our elementary row operations to a row echelon form of a matrix, and we can obtain a matrix in which every column has leading ones and zeros everywhere else. So here's what we're really wanting to happen. We want ones across the diagonals and zeros everywhere else, except for our answers in that augmented matrix. That's what we want. Because this will tell us, well, z equals this, y equals this, x equals this, and we won't have to do any more of that substitution piece that we did. So with this one, I want you to just follow along until we get to the point where we would do something new. That might even be the exact same matrix we worked with yesterday. It is. It's the exact same matrix that we worked with yesterday, but we keep going with it. So here's the deal. They went ahead and did our row echelon form until they got here. So this is where we would say z is 3. We wrote down 2 equations. We went back, found the other ones. But I notice here that if I were just to add this row to the second row, that this would be a 0. And that would be a good thing. So if I add this row, this will become 107. And that's something I can absolutely do. So we figure out a way to keep working with it and work backwards. Now there's lots of different orders that you can do it in. For instance, what they're doing here is they're saying, okay, here's what we saw. We saw that if you add the 1 to the -1 here, you get a 0. All right, so you do that. So this row plus this row, we would get 1, 0, 1, and 1. And that's what they got right here. And then they said, okay, now let's take care of negative row 3 plus row 2. Oh, they did row 1, so they went up to this row first. So -1 plus 1 would give you 0. -3 plus 1 would give you -2. And now the top row has a 1 to tell us x equals -2. Then they went down and said, all right, now if I add 1 to -1, I'll get 0, and 3 to 4, I'll get 7. And that gives you x is -2, y is 7, and z is 3. Now, typically, I will do this forwards with my triangle pattern and then work back up. And just think of back substituting. They went ahead and got rid of some stuff in the second row first. I usually go after the second row and then back to the first row as I go through there. But it doesn't make any difference. We'll all end up at the same place. So the calculator can also do this. Now, is this the one that we just had in there, or are we going to have to punch in a brand new matrix for this one? Cool. It's already in there. So here's what we're going to do. We're going to go find reduced row echelon form in the calculator. So this will be second matrix, math, and now we want to go down. Remember, row echelon form was a capital A. There it is. Get down one more time. Reduced row echelon form. So that's the one we want. And then we want to tell it second matrix, number 1A. Enter. Z is 3, y is 7, and x is -2. So we can check, make sure that everything's working well. When are we going to use this? When our matrices get really big. We'd like to be able, we definitely want to be able to do it by hand when we take the test, but I would think this would be like the biggest one that you're going to see on the test because they take a while to do in that form. So let's go ahead and take a peek at what they want us to do from here. So this says just using our calculator, if we punch all of this in, we'll get that reduced row echelon form, which we have right up here. Which of course, we don't have to do any math, and we know that x is 3, y is 7, and z is -2. So there's our x, y's, and z's. So this has 1x, 1y, and 1z as we go through that. So it is really nice for checking to be able to put that into the calculator. But this test does have a non-calculator and then a calculator portion on it. So be ready to do some of that by hand. This one says finding infinitely many solutions. We want to solve this system. Okay, well, we better make a matrix out of it. And we're going to, by hand, try to get ourselves to a reduced row echelon form of this. So let's see what we can do. Space here, but I don't want it so tiny that you can't see it. Alrighty, we need a place to start. And I'm looking at this and thinking, well, row 1 and row 3 both have really nice numbers, but row 1's already there, so why not just go ahead and use row 1? So what would you do first? Pick something that's going to get us some zeros times -2 and add it to row 2. After something for row 3. Okay. What do you want to do to row 1 to eliminate some stuff from row 3? Just a negative and add it. Let's do that. So far, so good. See anything you like, something you want to do? You want to flip rows or not? Okay, let's flip rows. Question artery. So,
You can cancel out the 2 bottom rows. So
yeah,
isn't that automatic?
that's kind of weird, isn't it? We don't cancel them both. Because remember, we can take a row and we can add it to another row, or take a multiple of it and add it, but that's going to make this. Zeros. What does that mean? It does. It means we can pick whatever Z we want. This was X, Y, and Z. We're not getting anything. We have X's and Y's represented up here, but down here, nothing for the Z's. So Z can be whatever we want it to be. So something, something Z is what we're getting. So here's what we would want to do. we would want to develop our x and our y. So we could figure out a way that somebody, if they were told what z is, somebody walks in and says, oh, for today, z is always 3. They could figure out what the actual solutions are. So what I would do is say, okay, can I do a little back substitution here to maybe make this a little easier? Or just work with what I have? Well, I think we could do a little back substitution. And I'm probably going to have terribly off space. Because if we take a negative 1 times row 2 and add it to row 1, things should get a little bit easier. So if we leave this alone, but now multiply it by negative 1 and add it to row 1. Let's see what happens. A little bit easier. So let's see what we have. This top equation says x plus z equals 5. We don't know what z is. So what we want to do is build a formula for x so that if somebody walks in and says, today z is 3, they'll be able to figure out what x is really quickly. Well, that means we need to know what x is all by itself. X is 5 minus z. Typically in the back of your book, they're going to put the variable first. So negative z plus 5. That way, once we find out what z is, it'll be super easy to figure out what x is. And then we go after y. Well, our y said y minus 2z equals 2. What should we do with that one? How do you get this to be something we could substitute in for y so that if somebody said, I know what z is, here it is. It would work nice. That's it. So that's what we do. Notice x, y, and z can all be found by just somebody coming in and saying, z is negative 1 just for today. That's what it is. So what we did was we rewrote this in that reduced row echelon form as far as we could. You know, we went as far as we could get everything with those zeros showing up there. But we do realize it is infinitely many solutions. And if you did this problem on your calculator, the reduced row echelon form shows up exactly like our reduced row echelon form. And that's because there's only one reduced row echelon form for any matrix. All kinds of reduced echelon forms, but only one reduced row echelon form.
For the y equals, would it be y minus 2z equals negative 2? Wait. Never mind. No, you're right.
You go after the last matrix?
Yeah.
That might be, yeah. Because there's so much to keep track of with these. You just have to kind of go, where's my last one? What did I have? Alrighty. Using matrices, we can solve systems of equations with more than 3 variables. So not just x, y, and z. W. More than 3 equations by finding a row or reduced row echelon form. The solution set may become more complicated. Okay, that's not a may. It will become more complicated. But let's do this one with a calculator this time. So let's set up our initial matrix. Let's get it in the calculator and let the calculator do the work for the reduced row echelon form. If there are no W's, what do I have to put in my matrix? It's got to have a 0.
On the test at all, is there ever going to be a time when you're given a set system and the numbers are going to be all flopped around, or is it always going to be like that, nice and neat. Like X, Y, Z equals.
Oh, you go by the order that they give you. That's how you write your ordered triple or your ordered, in this case,
It's
quadruple.
always going to be like ordered like that.
Exactly. So X's first, Y's, Z's, and W's. If they do move them around, then you just go in whatever order they gave you. Alrighty, I better find my calculator here. So I've got to get this one in. Oh, I'll just shut up because I can see everybody's just punching stuff in here. Uh-oh. I would have realized that when I went to the next number, wouldn't I? There we go. All right, let me make sure I'm in it right. Okay, looks good. Second matrix. Oops, got to get out of that window. Second quit. Second matrix. Math. And I actually can hit alpha B, and that'll make it pop up. It's a little bit faster to do it that way. Or you can scroll down. Second matrix. There's our baby. Bam. And that's the mess we get. Looks weird, right? What does this last row tell us? It is infinitely many solutions, but we've got another problem. We have extra variables, so we have to figure out how on earth we're going to do that. So let's write down what we just got here for our answer. Which was our 2, -1, -1, zeros. Okay, so what this means is X's, we're going to find something for. Y's, we're going to find something for. But Z and W, we're just going to have to leave Z and W. So with these, what we want to do is build a formula so that if somebody walked in and said, here's what Z is today and here's what W is today, they would be able to find X and Y. So we'll go after, I'll just go to the top equation first since it doesn't matter. It'll be X, no Y's, plus Z, bless you, plus 2W equals 1. So really what we just want to do is solve for X so that they can plug the numbers in. There's X. Again, somebody comes in and says, here's Z and here's W. This is what they are. That will find us X right away. Then the middle equation, no X's, but a Y minus 2Z minus W equals -1. So what do we want to do with that one? Okay, y alone, exactly. Oh goodness, I'm in the right spot.
So for the one, this was on the diagonal, how does that work with those senses?
That's the problem here. When we get all of these zeros, and if it's not a square matrix, what do? You do exactly what we just did. Where you say, all right, that means everything else is up for grabs. That means I'm going to have a formula for the x's because there's a 1 in the x column. I'm going to have a formula for the y because there's a 1 in the y column. But here,
So that the diagonal wasn't all zeros, but
we'd have to keep going. We would see what we could do. Well, what we want again is at the very least to have the 1s on the diagonal and zeros here. Now our goal is to also get the zeros up here if we can. But we just keep going as far as we can to get those solutions. Exactly. So we won't be able to find them. No matter what, W was going to be an infinitely many for this one because we didn't have a square matrix. And if we wanted to find all 4 of them, it had to be at least a 4 by 4 for us to start off with the coefficients. Otherwise, we're not going to be able to do it.
What do you do if you have 3 variables and 5 equations? Do you like just pick 3 of them to make a square? Or?
No, we wouldn't be able to because it would be a matter of where all of these fit in together. You said like 5 equations for 3 variables? We'll never put you in that situation. That would be something for your college matrices class. We won't push you that far at this stage. All right, so you can do the problems by hand. You can do them using the graphing calculator to get to where you need to go. And sometimes you can use it to develop, hey, what does the rest of this mean? Otherwise, we have other ways to solve. This is math. We have lots of ways to solve. So solving systems using inverse matrices is a great way to solve systems. If a linear system consists of the same number of equations as variables, then the coefficient matrix is a square. If the matrix is also non-singular, which means that its determinant is not equal to 0, it's going to have an inverse. It absolutely will have an inverse. So we can solve the system by using the inverse of the matrix. So, while I was thinking about Art's question, I keep thinking, well, maybe there's an algebraic way to do it that would be better even to do it than using the calculator to go from there. So, probably some algebra would be able to get you where you need to go. So, this one's kind of silly. It says solve a system using inverse matrices. Well, if we have to, yeah, we will. So, here's the deal. We have this matrix, I'll call it A, that just deals with the coefficients, and that's 3 and -2, and -1 and 1. And to get 3x minus 2y and -x plus y, we'd have to multiply that matrix by xy. Because when you multiply it, it would be 3x minus 2y and -x plus y. Now that's supposed to give us 0 and 5. So I look at this just as if it's algebra, and I think, all right, so let's make this x and let's make this b, and what it says right now is ax equals b. And here's what I know. If this coefficient matrix has an inverse, I'm going to have to put it right here because it has to be on the left side. Remember, that's important with matrices. Whatever side the A is on to start with, it has to be there when you get done. And multiply it times b to get x. So let's see. Does this one have an inverse? Remember how to check? Multiply, multiply, and subtract. Does it have an inverse? 3 minus 2 is 1. So 1 over 1. Now how do you get the inverse again? There's some stuff you have to do inside. Switch the main diagonal. What else? Negate. There it is. So 1, that scalar of 1 isn't going to do anything to that So that is our nice little A inverse here. Like I said, all we have to do is multiply this times B, which was this one, 0 and 5. And that will give us our little X matrix that we're trying to find. And that X matrix was X and Y. So let's see. We'll have 0 and 10. Oh, cool. X is 10. 0 and 15. And Y is 15. Now, can you do inverses on your calculator? We've been using the inverse button this whole time. Whenever we go to find matrices, we're hitting second and then inverse. Just don't hit second. Put the matrix in, hit x to the -1, times, choose the other matrix, and multiply. So that can be done on the calculator as well. By just A inverse of B, get them both in there, and multiply. So that was using inverses, and that's always a nice way to do that. But if you've got a determinant of 0, then you're in trouble because you don't have an inverse matrix. So invertible square linear systems, let A be the coefficient matrix of the system, and just like I did up there, you'd have AX equals B. So if the inverse exists, because A was on the left-hand side here, it has to be on the left-hand side of whatever it is that you're multiplying by in the future in order to make that happen. So this one says, let's solve a system using inverse matrices. Can we push this one in real fast? Let's see. So let's get our matrix in, and actually our two matrices. I better write those down. Once you have them in, you go back to your main screen, call up their names, hit the inverse button, and then call up the other name. And this is the part where if you don't like that it's decimals, or they haven't introduced decimals in the problem, you can always hit math, fraction number 1, enter, and it'll change it all nice into fractions for you. You don't have to do anything by hand with that, which is really nice. So, using those inverses, our solution was 118 thirds, and 14. Could have been done by hand as well, but we're definitely for time here. So, yeah, we gotta talk parabolas tomorrow and mixture problems, but 4321 me on just what we did today. And mostly I'm wondering about the calculator. How do you feel about putting stuff into the calculator to do it? Yeah, it's gonna take a little getting used to, isn't it? All that matrix stuff in there. Okay. So, you should be able to do most of the first day assignment.
And then you do the inverse times that.
Yeah, the inverse of the 3 by 3 times the other one with numbers.
Yeah, I actually put it
So she used this for B.
Now, let me do this. I'll move that one up because there's probably some of that now that you'll be able to get started on. Again, we didn't get to the mixture problem. We didn't get to the stuff about parabolas. So you probably won't be able to finish either one of these at this point. But do what you can with what we have. Follow the directions. If it says use a calculator, use a calculator.